Now that we have our understanding of the three subatomic particles, this section is going to look at how you actually can calculate and know the structure of the atom with respect to the three subatomic particles. So let's go ahead and get started. So reminder, we just discovered that atoms actually are divisible and made up of what we call subatomic particles: protons, neutrons, and electrons. The number of each subatomic particle in an atom and how they are arranged determines the properties of that atom. Have you ever stopped to think why some elements have some properties more than others? It all comes down to the subatomic particles, and actually primarily the electrons, which we'll see in topic 3. So the properties of all things material are determined by what subatomic particles are there, and more importantly, how many there are. There are so many different ways that we can represent an atom of a particular element. The most simplistic way is taking a look at the actual square that comes on the periodic table. Hopefully you're familiar with the general information that is portrayed. For example, the element symbol or the element name. Notice our periodic table does not give you the element names. But there's also some numbers on here as well. There's a whole number and then there's a decimal number. The whole number is referred to as the atomic number. And the atomic number, as we will see, tells us the number of protons that that particular atom has. The decimal number is known as the atomic mass. Sometimes we say also the average atomic mass. Same thing. And the atomic mass is not to be confused with what we'll talk about in a moment, which is mass number. The atomic mass, or average atomic mass, reported on the periodic table essentially is telling us, on average, this is what a carbon atom will weigh, or any element that we're talking about. So the element symbol on the periodic table gives us a lot of information. The problem is, it doesn't give us information for a specific carbon atom. It just gives us general information about carbon. To get more specific, we need to look at what's called isotope symbols, or isotope notation. So this is probably notation you'll see more often when we are referring to specific atoms of a particular element. So what you'll see is you'll see the element symbol, and then you'll see two numbers off to the left, the top number and the bottom number, which have the abbreviation or variable A and Z. So what does A stand for? A stands for mass number. Well, what is mass number? Like I said, the mass number is not the same thing as the average mass or average atomic mass. So what is the mass number? The mass number is simply how many neutrons and protons that particular atom has. So the mass number can be found by adding up those two subatomic particles. The bottom number, which is the letter Z, stands for the atomic number. And the atomic number, like I said, is found on the periodic table as the whole number. The atomic number tells us the number of protons, and it's the number of protons that tells you what element you're looking at. Every element can be distinguished by its atomic number. For example, let's take a look at your periodic table. If you were to take a look at carbon, every carbon atom, every single one, will have 6 protons. If you're looking at an atom that suddenly now has 7 protons, is it carbon anymore? No, you're now looking at nitrogen. If it had 8 protons, you're now looking at an oxygen atom, and so on and so forth. The number of protons is what dictates what element you're looking at. Finally, even though it's not in this symbology, if this particular atom had a charge, making it what we would call an ion, which we'll talk about in just a moment, the charge would be written up here to the top right. So taking a look at some examples down here, we have the element Cu, which is copper. Copper has a mass number of, an atomic number of 29, meaning copper has 29 protons. The mass number for this particular copper atom is 63. Remember, what does the mass number tell us? It tells us the number of protons and neutrons. So if you have 63 protons plus neutrons, and you knew of that 63, 29 of it was the protons, you could subtract these two numbers to figure out what was the number of neutrons that that atom has. Take a look at this example. You have beryllium, Be. This particular beryllium atom has a mass number of 9, 4 of which are protons, which means it has 5 neutrons, because that's the difference between the two. Additionally, this atom is actually an ion. It has a charge, and I know that because it's written up here as positive 2. Finally, you'll notice in this example, it actually does not write the atomic number down at the bottom. This is actually very common because a lot of people feel like it's unnecessary to have to write the atomic number as long as you know what the element is. So if I know that the element is iron, I don't necessarily have to write that the atomic number for iron is 26 because I already know what the element is. For our class, we're going to be consistent, and so we're going to write our isotope notation as such where it has both mass number and atomic number. Alright, so let's keep going. Reminder, the number of protons is what separates the atoms of one element from the atoms of another element. In other words, if you know the number of protons, you know what element you're looking at. For example, carbon, it has 6 protons, always. The number of protons is always the same as the atomic number. So out of all 3 subatomic particles, protons, neutrons, and electrons, protons is the easiest one to figure out. So let's take a look at some examples. I'm giving you 2 elements here, and I'm asking you to write the isotope symbol or isotope notation for the following neutral elements. Notice I tell you that they're neutral, so they're not going to have charges. Now I want you to assume a typical mass number. In other words, assume an average mass number, which means we're going to get that information from the periodic table. Let me show you what I mean by that. So let's look at the first example, silver. First thing I need to do is write the element symbol. Silver is Ag. And if I take a look at the periodic table, I can see that Ag's atomic number is 47. And so I'm going to write that down there at the bottom. Now, what do I write up at the top for the mass number? Well, since it's not giving me any information, I have to assume that we're looking at a typical, average, run-of-the-mill silver atom. So if I look at the periodic table for silver, silver's average atomic mass is listed as 107.87. Well, the mass number cannot be written as a decimal. It's always written as a whole number. Because remember, what is the mass number? It's protons plus neutrons. Well, you can't have a fraction or decimal of a particle. You can only have whole numbers of particles. So what I would do is I would take this average mass that's reported on the periodic table and just simply round it to the nearest whole number, which would be 108. So anytime the problem does not give you explicit information about the mass number, that's what we do. We assume it's just an average element, and we take the average mass, round it to a whole number. Let's do the same thing for chromium. Chromium is element Cr. The atomic number for chromium is 24. And the average atomic mass reported for chromium on the periodic table is 51.996. We're going to round that to 52. And so that would be the isotope notations for those 2 elements. Let's look at another example. This is a little different. Write the isotope notation for the element that has 14 protons and 17 neutrons. So in this example, I'm not actually telling you what element. We have to figure that out. So I notice that I have 14 protons, 17 neutrons. First thing I'm going to do is use the information about protons to figure out what element I'm looking at. What element has 14 protons? In other words, has an atomic number of 14. And that's going to be the element silicon, Si. And I'm going to write that 14 down at the bottom, since 14 protons means that's my atomic number. Now, what do I write up for the top here? This time, I'm not going to look at the periodic table, because notice it gives me the information I need, 14 protons and 17 neutrons. I'm going to add my protons and my neutrons together to get my mass number. And so that's the mass number that gets reported at the top there. Now real quickly, I want you to take a look at silicon on the periodic table. It's element 14. What's the average mass that's reported for silicon on the periodic table? It is roughly 28.09. So sometimes students see this discrepancy. They say, well, wait, hold on. The periodic table is telling me silicon is about 28.09, but this silicon atom is 31. Is that a mistake? Is that wrong? No. Remember back when Dalton said that atoms of the same element should all be identical? Well, that actually wasn't true. This is where we have what's called isotopes, which we're going to talk about on the next slide. But it is possible to have an element that has a different mass than what's recorded on the periodic table. Remember, the periodic table is just recording the average. It's saying, hey, on average, silicon atoms in nature have a mass of about 28. But this particular silicon atom just happens to deviate from that. It's 31. So if the problem gives you specific information, you have to use that information. Only in examples like this that we saw earlier, when it doesn't give us any information, that's where we can look at the periodic table to determine what the mass number should be. Okay? One other quick note on this problem before we move on. Sometimes students would have made the mistake of saying, okay, I know that the number of protons is 14, and I added them up to get my mass number of 31. And then they go to look on the periodic table to figure out what element it is. But they'll incorrectly look at the mass number to figure out the element instead of the number of protons. So what element on the periodic table roughly has a mass of 31? If you take a look, it's phosphorus. And that would have been incorrect, right? So mass number does not tell us what element we're looking at. That is not the correct way. It's always the atomic number that tells us the element. So like I said, isotopes are going to be situations where you have an atom that is of the same element, but it weighs differently. It has a different mass. In other words, the mass of an atom, which comes from your protons and your neutrons, it's going to be different. So not all atoms of a given element are identical. We saw an example of that on the previous slide. Most elements, in fact, in nature actually have a mixture of at least 2, if not more, isotopes. So the definition of an isotope is an atom that has the same atomic number, which means it's the same element, but it has a different mass, which ultimately then means it has a different number of neutrons. So let's take an example. Look at these 3 atoms down here. You'll notice the protons are the red positives and the neutrons are these little yellow circles, and that would represent our nuclei for these 3 atoms. Notice all 3 of these atoms have 1 proton. 1 proton, 1 proton, and 1 proton. So what's the same between all 3 of these? They are all hydrogen atoms. But what's different? It's the mass number that's different, right? The mass number is your protons plus your neutrons. So this first atom right here has a mass number of 1. I could write that just like that. This second atom has a mass number of 2. So I could write it like this. And this third atom has a mass number of 3. And I could write its isotope notation like that. So notice they all have the same thing in common. 1 proton, which means it's the same element, but it's the mass numbers that are different. They all have different number of neutrons. And so I would say that there are multiple isotopes. Which one of these would we consider the normal or regular hydrogen atom? Well, if I look on the periodic table, I notice that hydrogen's average mass is 1.0079, meaning the average mass of a normal hydrogen atom is 1. So that means that this atom right here is what we would say the normal hydrogen atom. And it's these ones that we would consider to be the isotopes. All right, now notice the naming. The regular atom is still called hydrogen, but the other 2, they have these special names, deuterium and tritium. These are actually Latin names. It's still hydrogen, but they have special names for hydrogen, considering that they have different masses. Well, scientists quickly realized that most atoms in nature, most elements have isotopes. So we gave up calling atoms by different fancy names, and we actually just call isotopes named by the symbol and then dash whatever the mass number is. So we would say, for example, this isotope's name is uranium-235. So now we just name isotopes not using fancy Latin names like we did for hydrogen here and here. We just name it based on its name as an element and then its mass number. So to remind ourselves, if the mass number is not given, like our very first examples with silver and chromium, assume a typical mass given from the rounded periodic table value. If the mass number is given, or if the number of protons and neutrons are given, such as we saw with silicon, we need to use that value. And if the mass number is different than on the periodic table, it's an isotope. We're going to continue on with ions in the next video.